Sí, sí.
¿De qué hablas?
Google Meet. Google Meet.
Ah, ¿en serio? Uy, qué cagada. Bueno, está bien.
Ya me lo había aplicado.
Okay. Good morning, everyone. Let's start our last class. So today I will speak about the last part of the analysis of the labor networks. So I will make just a short note that in the class of yesterday, we spoke about the reduction techniques, yes? So I showed you how to extract, not yesterday, the day before yesterday, sorry. So I showed you how to extract the industry space from the networks. And then in the classes that I sent to Tiago, you will see that there is another techniques how to explore these networks. There is another way to make the networks reduced is to use the threshold models. So I left them on the slides because I didn't have enough time to show you this. And this is the way of working directly with the flow networks. So you basically look at the links and the absolute values of the flows, and you start to cut the links with the flows. You put the thresholds and you say that I'm not interested on the flows that contain very small number of switches. And then you look at the networks, at the network that is left. Okay, so what you basically look for is the corridors of the flows with the maximum weight. Okay, so and there I also left you the Shiny developer, so you can go there and you can play with that because it has all the possible ways of exploring the network. Okay, so it is just left for exploring. So today I want to talk about two things that are left for the analysis. On one side, these are the distances, and on the other side, what are the communities that are found in this network. So why are the distances? The distances I will be using in order to compare my networks, okay? As you are remembering, we have the 24 different networks, one for each year. So I have a series of years, so I have a temporal observation. So, and we saw that there are different structures that we observed. So my questions was what kind of techniques I can apply in order to compare the structures, yes? So, and after the different things that we have been trying in the group, we discovered that we can use the distances to compare the structure, because what I'm interested here is the connections between the sectors. So I want to discover, I want to analyze how the connections between the sectors have been changed from year to year. So in particular, I go back to this slide. So we saw that if I look at, so I picked several examples from different economic periods. And then we saw that if I look directly at the network structure, I don't see basically the differences. But then if I looked at the heat maps, then we saw already that the structures are quite different. So what I want to compare now are these heat maps between the different periods. But I will be checking these heat maps from year to year, okay? So this is the exercise that I want to do. So, and how I will be doing that? There is a very nice framework that is developed by Donnat and Holmes in 2018. This is the paper. This is a paper tracking network dynamics, a survey using graph distances. I recommend it very much for you because they developed an approach to compare a network of nodes aligned at different moments of times. And this is exactly what I'm looking for, okay? Using the fundamental matrices of the graphs, which are exactly what I'm using, because these are the matrices of the flows, where I have the nodes and the links are the flows. These are my transition matrices associated with these networks. Different metrics and dissimilarities are used for their comparison through the analysis at different scales of their topological structures. So this is exactly what I want to do. And I want to and they developed this approach to compare networks at 3 different levels. At the local level, intermediate, which are to discover the differences at the method structure, and at the global structure. So I recommend here, if you click here, you will go directly to the PDF article, okay? So what are these distances? Some of them you know very well, because this is just a Jaccard distance. So I will be looking at the growing connectivity analysis. On one side, you have a Jaccard distance, which is just measuring a total change of connections and node. So I take the first order connectivity. I will look at the sector, and I'm interested at the immediate change of the connections, okay? Then I have a polynomial distance. What is a polynomial distance? I will be expanding neighborhood with interaction. So I have a of order 2. So I'm interested in the change of the structural changes of the connections of my neighbors. I will be looking at this a little bit further. And then I have another distance, which is a spectral distance. Are you familiar with that? So, and a spectral distance, what does it say? This is about the propagation of information from each node to the rest of the graph. These are the frequencies. So this spectral distance will give me the global information of the structure. And
how do you traverse the graph?
Pardon?
It's not important how you traverse the graph.
What do you mean by traverse the graph?
How you visit different nodes.
We will see now.
Okay.
Just give me a minute. And then maybe if I don't answer you, you will ask me again. So, sorry. So what do these distances allow to discover? They will allow to show the interconnection stability regimes and anomalies and transitory transition periods with respect to where this distance is very small or very large. And this is exactly what I want to see when I compare it from year to year. So I will not show you the mathematical development of each distance, because otherwise I won't be able to show you the second part. But in this article that I put on the slides, it is very easy to consult. And in any case, we can discuss if you want to know a little bit more after the class. So the Jaccard distance, basically I look at with any graph like this, allows to identify changes in the network at the level of my local interaction. So if I am a node here, what I look at my first neighbors. So I pick up the sector, yes, and I looked to evaluate the rate of rearrangements of my connections with other sectors, okay? So I do it sector by sector, okay? So the coefficient can be interpreted as the proportion of links eliminated or incorporated with respect to the total number of links that appear in both networks, because I take the 2 networks because I compare 2 years. So I do it from year to year, year to year, year to year, because I will be comparing all the 24 networks, okay? And of course, the Jaccard distance, it's between 0 and 1, and if its value is close to 1, it indicates a complete remodeling of the structure.
This metric is used to calculate similarities?
Yes.
So you are looking for the self-similarity of the node in different times?
Yes.
Okay.
Okay. Very important remark. These distances at this analysis I will be doing when they are binaries. So I'm not interested in the flows, because what I want to see is just the arrangement of the structure. So I don't really care of the flows. I don't care of the weight of the links, okay, for the moment. What I want to see, what happened with my connection. And I can do it because I already saw that all of the networks that I received, they have a very great, very high reciprocity. So So that's why I can apply this approximation. I can just compare, and I can just make this analysis on the binary matrices, okay? Polynomial distance, and here I go, I will not look at as a Jaccard, I will look at the second order neighborhoods, okay? So it's based on the use of the power of polynomial. This is just how there is an expression that I use the polynomial to calculate on the matrix of distances. And it is related to the local topology of the graph through the coefficients of this polynomial function, yes? So it represents the path from node I to node j through the k steps, okay? And it allows to quantify differences between two graphs of the connectivity structure that each node presents with a neighborhood of nodes with which it has direct exchanges. So what I want to see is that it's not only that I change, but I'm interested if the structure of the sectors with whom I am connected, how much stable the other structure, the other connectivities of the sectors is, okay? So it's like I'm interested in this interconnections. And then, of course, the spectral distance is characterized, the state, through these eigenvalues. So I take the eigenvalues of the matrix to detect the changes in global and intermediate structures. So why should these eigenvalues characterize the state of a graph? Yes, and better. Because the eigenvalues characterize its topological structure, and in particular, how the information is localized at a particular node and how it can propagate. So for the mathematical representation, I invite you to look, because otherwise, this is why I did not put it here. If you analyze the eigenvalues of the matrix, you can really relate it to the stability of the network. So there is a direct relation. So the spectral distance will be defined as a distance between the functions of the spectrum of the eigenvalues of the matrices of the both graphs. So as I said, these distances, when I apply the three distances to the 24 years, to the 24 networks, yes, what I will be extracting from this analysis is that I will be able to analyze, I anticipated a little bit, the stability regions. So I will be able to analyze and see which years will behave similarly, yes, and where and which years will be showed as a very different ones, because these distances will show it to me, okay? So I will be see the anomalies and transitions. And why do I want to do that? Because when I showed you this evolution of transitions, and I said that when we spoke with economists, they just put together several periods, yes? And they showed this is a convertibility, and this is post-convertibility, and this is recession. Some of the crisis periods, years, they were in sight. And these are clearly the years of transitions. So I want to see if this analysis will extract it from there, because for a clear opinion, this has to be taken out of the analysis and treated as a special subperiod, for example, okay? So this is what we want to observe as well. And what would be this useful for how this can be useful for the employment transitions? Because they can characterize and monitor intersector connectivity and identify these connectivity regions, yes? When I do these distances, yes, when one is doing these distances, usually it is accomplished with what is called metric multidimensional scaling, MSD. This is some sort of PCA. Yes, I just put in blanco. Principal component analysis, okay? So it is it's a classical nonlinearly, it's like a dimensional dimensionality reduction techniques, and based on the decomposition of eigenvalues of this distance matrix, yes? And we will be using it in order to map the proximity of the different networks in these components. So we will be looking at the components of this PCA and see which components represent better these distances afterwards, okay? And then we will be analyzing the results of the distances in terms of the MSD, okay? So what is the, this had to appear afterwards, but anyway. So for example, this is the Jaccard matrix, the Jaccard distance. So what do I draw here? Here we have 24 years from 96 to 2019, and here as well, yes? So what do I observe here? I see that clearly we have two large periods separated. Do you see that? Yes. So we can see that between 96 and 2000, this is one group, yes? And then we have another one, which is from 2004 and 2018. And then we have this much darker, almost red. And then we have a year 19, okay? So for example, this group from 1906 to 2000, this is what corresponds to convertibility. So here, the years show to be very similar, okay, how they behave, and the structure in terms of the behavior, in terms of the structure. I speak about the structure, the connections, okay? And the same I can observe here. So all this block also present relative similarity in these consecutive years, yes? But they are different with those periods that are here, yes? For example, this is the crisis, so 2001 and 2003, and this is another different year, 2019. So, and that's why there appear differences. So they are with a different color. When it's much more red, the distances are much more different. And then here, what I plot the results, they are mapped, the distance matrix is mapped into the first two components of this PCA analysis, okay? So I try to show it. So what they do, because these two first components, they capture the greatest variability of this matrix. And between these two components, they accumulate almost 28% of this total variability. And so what do I observe here? So here I show the different transitions. So what I observe here is that it orders the years of different groups, and it separates the years of transitions. For example, here you have 2001, here you have 2019, and you have a different distance. So it clearly separates it, okay? And it also groups with respect how they are similar between themselves. If I show, for example, if I show, for example, the spectral distance, yes, I also observe, I also observe two large groups of periods. For example, here I have 1906, 2005, and then I have 2007, 2018. And so these groups of labor mobility are identified. But here I have 2006, quite different. That is differentiated from the rest of the groups, yes? And also I can see how they are arranged. And again, 2001 is separated as a year of transition, and as well 2007. So, and these are the results of the polynomial distance. So, as you can see, that the three distances, what they show with respect to the initial grouping of the years, yes, what they are showing is that they are separating the transitions, okay? So what does it say is that it suggests for us, here I show again that how the MSD analysis maps into the components. And it is possible to confirm that the differences in the structure at different levels of analysis appear to represent different regions. And what is interesting is that what it offers to us, and it was discussed in a very interesting way with economists, is that macroeconomic analysis showed this. So they offered only 4 periods, yes, that they said that these are just convertibility, post-convertibility, local stagnation, and recession. And after that, we show that applying these distances to analyze the similarity between the years, we obtained a little bit different aggregation, okay, between the analysis. So you truly have to take out the transitions from the grouping the years in order to analyze and make some kind of analysis when you want to analyze the years and the similarity between the years, okay? So this was a very interesting finding for them because they never analyzed it at this level. So what I want to show now, there were some more extra work done here, but I just don't want to present it because this was like the main idea to show that the framework that was developed by Donnat and Holmes, which permits to analyze the network structure at different levels of connectivity, it is very useful to analyze networks that change the structures. So this was just to show that it can be used for any kind of networks. So, and it's very easy readable and it's very easy to apply. So then what I wanted to talk is about the communities. So of course here the sectors, the industries, they are reaccommodating through the job switches and they form the communities. So of course we too also started to look what kind of communities forms here as well. Apart from the fact that we analyze the industry space in the other class, here as well you can analyze communities at 2 different networks. You can analyze it at the flow network, just looking directly at the flows and to see how the industries reorganize between themselves. And also you can directly take the industry space and see what kind of communities are there. But since we already looked at the core decomposition of the industry space to see how many industries are inside each core, so I decided to look here what kind of communities would appear if I look at the flow network directly, okay? So I know that most of you are already working with communities, but I also know that some of you have never heard of communities, okay? So I decided to balance a little bit the presentation, so I talk a little bit of things that probably you know, but some of you have never heard of. So what do we know about communities? So this is a very nice example. I really like this, this network. It comes from Belgium. It's a real world example. And this is, everybody knows that Belgium is a bicultural society. I think you are in Belgium, yes? So probably you know very well this network. So where they speak 2 languages. Yeah, they speak Dutch and they speak French. And what is interesting is that, well, here they're saying 59% of Belgians, they are Flemish. And another 40, they are Walloons, and they speak French. So as multi-ethnic countries break up all over the world, yes, everyone is asking, how did this country foster the peaceful coexistence? You tell me, is it true they are peaceful? No, but we take it as a fact. Since 1830. Is Belgium a densely knitted society where it doesn't matter if one is Flemish or Walloon? So we're asking that, yeah? The answer was provided by Vincent Blandel and his student in 2007, who developed an algorithm to identify what would be the structure of this community in Belgium. So they started from the mobile call network. So they collected this data, yes, and they placing individuals next to whom they regularly called on their mobile phone, okay? The algorithm revealed that Belgium's social network is broken in two large clusters. What does it mean? That means that individuals in one of these clusters, they rarely talk to another ones. So Flemish, they only talk to Flemish. And the other ones, they only speak between themselves. So they never call to each other. And that's how they peacefully live in this country. And what is interesting is that there is here, it's like a bridge. Here is a zoom of this bridge. This is a very small little cluster, yes? The origin of this separation, so this is like a small where there is like a little mixture. But basically you have two communities, and they are never mixed, okay? And this is another example. That's how the theory of communities started to arise. What is called Zachary's Karate Club. This is a social network, a small one. It has only 34 members of Karate Club. And this is a social network that received most attention in the context of community detections because many different models appeared after this network has been analyzed, and a lot of different community detections methods appeared, in spite of the fact that it's a very small network. So what this network tells us, this is a club, small size, it's a small network, where each member knows everyone. So this is a very interesting fact. And to uncover the true relationships between the club members, the sociologist Zachary documented 78 pairwise links between these members. So the interest who regularly interact outside the club, okay? So everybody knows everyone. The interest in this data set is given by one singular event, a conflict. The president of the club is in conflict with the instructor of the club. So the club is split in two, okay? And about half of the members followed the instructor, and another half of the members, the president. So again, we have the two communities, okay? And so this is the structure. And today, communities finding algorithms are often, as I said, based on studying this model because it's a very easy treatable model in terms of the number of the nodes. So here I leave for people that, for those that have never worked with communities, some notions. So what are the communities? How many communities can be? The communities is inside this gray area. And what are the communities? And how can we partition that? How we count the degree inside and outside, and the internal link density, yes? So these are just the notions. I will not go through that. So what would be the basic algorithm to extract the groups when we have the network? This would be the hierarchical clustering, yes? So we have the two ways of proceed with hierarchical clustering. We have agglomerative algorithms and divisive algorithms. So it has to do with the name straight away. Agglomerative, they merge the nodes that have the high similarities, and they put them in the same group, okay? And divisive, they isolate communities, yes, by removing low similarities between the nodes, okay? So what they do, they generate hierarchical trees, okay? So And this is what I said in the other day, that basically to decide the group similarities, you have 3 approaches. You have the single, complete, or average cluster similarity, and you basically use for the similarities the distances that you can have, the Jaccard distance, you can have the Hamming distance, you have different kind of distances that you can use in order to fix and see how far or how close are the nodes. Here I leave you a small example that you can try. So here you have a single linkage, and here you have a complete linkage or the average linkage between the nodes. Okay, so this is just I leave for some notions, and this is the tree, and you build the dendrograms. Okay, so here you organize the groups with respect to the similarity between the nodes. So what we will be doing as many of you, when you did the presentations, you already showed different and mentioned different kinds of algorithms to find the communities, and we already know that there are lots of algorithms to find the communities, and there is a community that works on different methods to build the communities. So this is a very nice, interesting subject. So in order to find the communities in our labor networks, we worked with the algorithms which is called Leiden algorithm. I don't know if anyone knows about Leiden algorithm. Good, so I bring you something new as well. So it identifies structures based on the modularity, of course, as a criterion quality function, but there is a small difference with the Leuven algorithm.
What is the modularity?
Modularity is some sort of a quality function that is based on it's a function that you optimize when you cut the links and you group the nodes, okay? But you have to think it as a function to optimize, as a quality function to optimize. Huh?
Like an entropy?
It doesn't work exactly like the entropy, but you can make an analogy, yes. So this indicator measures the strengths of a partition of a network into models. So, and let me go straight to the, for example, most of you already know the Leuven algorithm, yes? So here I just put how it works. So it's a local moving of nodes, and then it's aggregation of inside the network. So in the local moving, so here I have it as well, yes? So it starts from a singleton partition in which each node is in its own community, and then it moves individuals from one community to another to find a better partition. And then it creates a network. So here, again, for some details and how this algorithm is implemented, so I don't want to stop on the details, yes, because I want to go to my communities. I'm more interested in my communities that we received. So here is an algorithm that we implemented. So it's called Leiden algorithm. It is in this paper actually it's called from Leuven to Leiden algorithm, and it is shown that it starts quite in the same way as a Leuven, but it gets the better partition. Because they argue that when you use the Leuven algorithm to build the communities, it's not always the best way to obtain the groups. Sometimes it's not the best partition. So they optimized it, and this is just how it works, so the details you find here. And they showed that this is a better algorithm, which has quite a similar way how it works, and it gets the better way of partitioning the groups and organizing them into the communities, okay? So I recommend you this article. So here are what I wanted to get. Huh? If network has to be directed? Sí, sí, perdón, no escuché. Okay, so here I wanted to bring you to this result. So these are, let's start from here. So these are different networks that belong to different periods. So here is in the period of 96 to 02. So they are from different periods that we were looking at. And these are the communities, sorry for, where the size of the nodes is proportional to the size of the employment sector, okay? So how much employment it absorbs. So you don't really, I don't make a zoom to analyze it, but there is a nice representation like this where you can see the evolution. So in which way you can see evolution? That if I put here what are the communities per each year period of the consideration, then I can see how they are reorganized from each period to another. So I can see if there is a reorganization of the communities. Okay, so this is a very nice representation. So the main result is that when I looked at what kind of communities we received, basically we have that in the years that are in the period of convertibility, and then this small period that is 1920, which is the recession. This is quite, I'm not talking too much about that because I have small data set there because it's only with respect to the others. So, and what's more, there where I have in Argentina in particularly, it's a very special data set because we have a change of government and also the beginning of the pandemics. So it has to be taken very carefully to analyze. But we have basically observed 7 communities. Communities, yes. And then in the other periods, we have 6 communities, okay? So it doesn't go much more than that, okay? So what are these communities is that it is interesting to see that the largest and the most principal one in all this temporal evolution, where we have main groups of activities, we have that the main one is the industrial nuclear. This is the core that we always observed when we analyzed the structure of the network, okay? And we can see that inside this nuclear, industrial nuclear, we have these activities. For example, we have automatization, we have petroleum, we have construction, and etc., and so on. And then we have another second nuclear, which is nuclear of services, okay? This is the second one, which is the big one. And then we have the smallest. The other ones, this one, for example, has educations, it has telecommunications, pharmacies, and it's aéreo, etc., okay? So what is interesting here as well is that I can go now inside each communities para ver what happened. But fíjense that here the structure is quite similar, except, of course, the last year when we have the organization of the communities. But again, I take this period apart, okay? So if I go inside the communities, I want to see what happens there. And I want to analyze, since I have a labor network, what I will be doing, I will be analyzing in terms of how much of employment it absorbs, yes, how many sectors are inside, because then once you build this, one thing is just run your algorithm, which now is very easy. You don't even have to program this algorithm laden in order to find the communities. You just call this function, and it runs. So it doesn't even take so much time. But then what you have to do is just you have to go from that level of abstraction to your problem. And then you have to interpret all this in terms of labor and try to understand what happens inside of each community. Is not it? So that's where sometimes the problem comes. And then you have to speak with lots of economists and people that work at the ministers. So that's where I am. So, and here what we have, for example, this is just an extraction of a huge table. So here where I put the number of sectors by their letter of classification inside each community per period, okay? For example, this is my first period. So this is what I do is I take this, for example, yes, and I go community per community, and I look what is inside each community, okay? It's fine? So let's see what is there. So I have 7 communities, okay? And inside, and I look at, and
These are communities inside the community.
this is, for example, what I do is, what did I do? I don't know what did I do. I did something very different from what I wanted to do. What I do is, for example, in this period, yes, I said that I receive is this one. I look here, see, in this, and I say that I observed 7 communities. Okay, so these are 7. So I want to see what is there inside, because this here I have lots of nodes. ¿No es cierto?
Yes.
Because these are this community is called industrial nuclear. So I want to see what is inside there. And then I want to see what is inside there and what is inside there, and see how many sectors are inside and how much of employment it absorbs, okay? So I want to see the details, economic details of this community, okay? It's fine? Yeah.
So is there like some kind of threshold that you set to see how big the community has to be? Like if you set a higher threshold, you see smaller communities?
No, this is the algorithm laden that did that. So the laden, when it works, there is a modularity function over there that is optimizing, and it groups, and this is the result of this algorithm. Yes, I don't put the threshold there.
So the Leiden algorithm stopped by
Exactly. When the laden stops, it expulses 7 communities. And for example, here, it only gave me 6 communities, okay? I don't use any threshold, yeah, because otherwise it would be induced if I put the threshold, okay? So let's see if I want to see what is inside here, okay? So I go there and I see that I have 7 communities inside the nuclear, which is industrial. The first line is the black one. These are the letters. This is the classification. When I said that it can be manufacture, it can be fishing, it can be, this is the way how the economic activities are classified, okay? So here I see that I have, for example, let's see this one, the letter D, which is manufacture. How many sectors are inside? 122 sectors, yes? This is the most numerous. So that means that this sector is disaggregated into a greater number of communities. So, for example, in the first one, I only have 71 sectors of this activity. Do you understand what I'm saying? Yes? Okay. Then, for example, I have 7 sectors that come from the letter G, which is another economic activity. I don't remember. We can look at it. I think that, no, I don't have here the legend. And then I have, this is another, the second one that is the most aggregated. And then I have this one. But what I want to draw your attention to is the fact that those economic activities that are the most numerous, yes, they are disaggregated, and they tend to be concentrated in many and participate in many communities, okay? And the ones that are less disaggregated, they will be concentrated at most in one community, like this is the case, or in two. For example, N. Okay? So those economic activities that are not very much disaggregated will be in one community or two at most. But the ones that are huge, like we already know that manufacture is a monster, will be participating in each community, which has sense because it has afterwards you have to analyze in terms of demand oferta, offer and demand. So how much and what kind of people they need for their service and their job offers, and how much and whom they are sending to another industries. Okay, so there is always this trade-off. And another interesting result is that this is in terms of participation of the communities, of the sectors inside the community. But you can also look at the participation of the employment. How much of an employment is inside of each community, okay? And this is also, for example, you can see that the first nuclear, o sea, the first, this big nuclear industrial nuclear, in this year captures about 21% of employment, pardon, okay? So here you can also analyze in terms of per year, in terms of how much of employment has each community, okay? So what you can conclude afterwards, is that this analysis can show you the structures with a certain degree of permanence in time, and also differences that show how they evolve with different with time. And of course, this period you just have to look differently. And then we saw that two stable communities are clearly distinguished. One that forms a group of sectors with high interactions, and it functions as a center, as a core. So that's what we saw in each analysis. And then we have others that always serve as a periphery. So at least this is what is implying for the labor of Argentina. We also did an analysis that we compared the same kind of data to the German data and to the Sweden data. And in spite of the fact that the volume was different, we didn't observe very much differences in terms of organizations at the level of the structure, which was a very nice finding. So let me stop here, and I will invite you, because I liked very much what you did, Chris, at your class, so I did the same. So let me show you that these are the two people that I work with, and these are two. Sergio is economist, and he did his master degree in data sciences. So this is the guy we are doing a lot of data processing. And this is Daniel Heyman, who is economist and physicist. So we are discussing a lot of economic stuff. And I'm working at the Instituto Interdisciplinario de Economía Política. I'm a physicist, but it's been already almost 13 years that I work with economists. And this is our lab, so I invite you to look at what projects we are doing there. So there you will find a lot of financial stuff. There are lots of financial networks that we are analyzing. And whenever you need any kind of information, you can contact us there. So thank you very much. I hope you like that. Probaste ovation problem y no funcionó. I noticed. Tendrías que probar otro umbral.
Experimental ovation.